Hello, Mr. Ryan, right?
Yeah.
What have we talked about yesterday in the last lesson?
What do you think? Tree. Binary search tree.
Yes, what are we going to do with the binary search tree?
Find the node which is the closest to the target.
Yes, we're given a target, we're given a binary search tree, and we want to find out the node which is the closest to the target. And if there are multiple answers, we want to return the smaller one, right? And we talk about the recursion, right? The key idea is that the closest node must be the root node or in one of the subtree, right? It can't be in both. Make sense? Does it make sense?
Yeah.
For example, like if we want to find 4.5 in this binary search tree, can I say that it must be either the root node or in one of its subtree? One of its subtrees, right? So why do I keep mentioning one? Because I can use the binary search. 4.5 is smaller than 5, so I go to the left. I don't need to travel the right. Okay? If I want to find the 6, it's either 5 or on the right, so I don't need to travel the left because it just goes further, right? So look, 6. Now I have 5. So if I move to 3, there's bigger distance between 3 to 6 than 5 to 6. Make sense? Yeah? Okay? So that's the key idea of this binary search. This is the iterative binary search. Okay, and we can implement this using recursion as well. So how do we implement recursion? This one to recursion. Define f root target. If not root, we just return infinity. If now the target is smaller or equal than root of value, so this target, right, this is 5, this is 4, this is 6. I want to find a t. If t is smaller than that, so the answer must be here, right? Yeah, or this one, right?
Yeah.
So answer equals f root of left. Okay, else answer equals f root of right. Okay, so f root of left, f root of right is just recursion, returning the closest node in the left tree or right tree, right? And we have to compare with this root node as well. So return, here we just return minimum. It's either this root node, right? Root dot value or the answer, and we want to use the lambda function. Key equals lambda. Key equals lambda x abx x minus t. Okay. Key equals that because that we want to compare the distance. Min function returns the minimum. We are not comparing the value itself. We are comparing the distance. So that's why we need to supply it with the lambda function, which as a key, compare key. This is basically saying that the root of value minus t absolute value and answer minus t absolute value. Which one is smaller? And give me that. Okay? This is the recursion version. Okay? Make sense?
Yeah.
We mentioned about the in order, right? Why do we need the in order? What's so special about in order on a binary search tree?
Because it goes in order.
Yes. Look, this is binary search tree, right? 5, 4, 6, right? Something here is smaller than 5. Something here is bigger than 5. So if I travel the tree, the left tree first, right? I visit the node smaller than 5, and then I visit the 5, and I visit the node bigger than 5. I recursively doing this on the left tree and the right tree, so I get the in order, I get the sorted list, right? So the in order thing, we use min function to get that, and we talk about the difference between the yield and the list, right? So let's write this in order thing again. Define in order root. If not root, or if root is none, return, right? And then yield from in order root of left, yield root of value, and yield from root of right. Okay, this is the using the yield, and we can use this function to do similar. If you want to return a list, right? Return a simple list, and answer equals in order root of left, answer plus equal root of value, and answer plus equal in order root of right, and then return answer. Okay, this is the alternative implementation using the list as a result. Right? Using the yield gives the O1 space. We talk about that, right? Using the yield. Yield thing is like a promise. I don't give you all at once, right? There's a difference here, right? Because if we want to convert it to Inorder, using the Inorder Traversal to return a list, right? So for example, like that tree, binary search tree, if we perform this Inorder Traversal, that's 1, 2, 3, 4, 5, 6, right? 7, it's in order. I want to find 3.5. Return a list that will generate list in order. That means that it's O(n) time complexity. By using the yield, I'm not generating the list. So instead, I'm pointing out to the beginning of the iterator. I move. I'm moving to the place that between the previous one and the next one. So I know the closest node must be in this node or that node. Then I can simply return. I don't need to keep traveling, right? Suppose this goes to 1,000,000, right? So that's the difference between OK and ON. Okay? Make sense? Yeah, okay. K is the number of steps we travel until we find it. This is what I've covered yesterday. So today we're going to talk about this iterative version. Okay. Remember we talked about the breadth search, right? Level by level. If we change the breadth search queue to stack, what do we get? Do you still remember? You know the breadth search? Yeah, level by level. If we change the queue to stack, what order do we get? Pre-order or reverse pre-order, remember? Yeah? But now we are talking about the in order, right? In order. 5, 3, 4, 2, 7, 6, 8. Okay? Define in order. This is the iterative version of in order. We talk about a recursive. Recursive function is simple, it's trivial, right? It's very simple to write. Visit the left tree, visit the node, visit the right tree. How do you visit the left tree and how do you visit the right tree? Recursion, calling itself. In order, root, target. We need a stack, right? We need a stack. So while root, while we do the another while root as stack.append. What's stack?
Stack. First in, last out.
Yeah, first in, last out. It's like a pile of dishes.
Pancakes.
Yeah. Append left and root.left. So root equals root.left, okay? Root equals root.left. Yeah. And then this is a template, right? And then now I get a value. Root equals stack.pop. And then I need to walk to the right. Okay? Okay, let's use this, right? So at the beginning, nothing, right? Stack. Here, I'm here. Okay, while I haven't reached the list node, I put a root in, which is 5. I can go to the left, right? Go to the left, which is 3. I can go to the left, which is 2. Okay? Then I go to the left, and it's nothing, right? It's nothing, I go out, okay? Now, okay, so st.pop, so which is 2, right? 2, yeah. I take it out, and then, okay, root equal root.right, okay? Can I go to the right tree of the 2? No, right? I go to it, it's nothing, right? It's nothing. Why root or stack? Here there's a problem, okay? So now root equal root.right, go into the right, okay? Now the stack is not empty, so we keep doing, okay?
Why there are 2 whiles?
That's the good question. Yes, this one, we're just pushing the left, go to the left, pushing it to the stack. And then, because we're pushing to the stack, look at 5, 3, 2, right? And the reverse will be 2, 3, 5, right? Am I right? Yes? That's the beauty of the stack, right?
Yeah, but what's the first while for?
The first while, because we haven't finished the right tree. When the stack is not empty, we need to keep exploring, right? We need to keep exploring, because if we will go to the right, we have to keep exploring. For example, there could be some here, right? Yes?
Yeah.
So this is the thing, right? So look, 2, go to the right, nothing. 3, take a 3. Take a 3, then what happened? Take a 3, we go to the right. And then put a 4 here. Make sense? Okay, so this is the iterative version of the in-order. The key idea is that if we have left trees, if we have left kids, we push the left kids to the step. Because in the reverse, when we take it out, it'll be 2, 3, 5 increasing, right? But we have to go to the right tree as well. So when we don't have the left tree, we take one from the stack and we go to the right. Okay? And then again, if they are left tree, we keep pushing. Right? Because this here, this is bigger than this one, right? Okay? Any questions so far? So now if we're using this, how do we solve this? How do we get the closest node? We have to remember the previous node, right? We have to remember the previous one, like, the previous 3, the previous 4, previous 5, right? So if this node is between the previous node and the next node, the current node, then we return it, right? Previous node equals minus infinity. At the beginning is minus infinity, am I right? Before we go to the right, root equals root dot right, right? Before we go to the right, we remember the previous one, which is previous equals root dot value, okay? Right? And then before we remembering the previous node, we have to check here. If the target is bigger than the previous value and smaller than the root dot value, smaller or equal than root dot value, then we return the minimum of previous one and the root dot value, and the key will be equals this, the same thing, right? Okay? Key equals lambda x abx. Key equals lambda x abx x minus t. Okay? So this is saying that if I'm here, if my current node is between two neighboring nodes, the closest node must be this one or this one, and whichever is smaller, mean. By giving this
what if you only have one node?
That's very good counter case. If we have one node, does it work? If there's only one, that's okay because you come here, right? And then if it's bigger than the minus infinity, the previous node is minus infinity, and then previous and the root of value, obviously the single node wins. Does it make sense? Yeah. For example, like if you're given a 7 and you're given 100, the target is 100, right? Always the single node wins because the previous value is minus infinity.
What if the target is infinity?
Good question. The target is not infinity. You can't give a target infinity. Infinity is not a concrete number. We will talk about the limits later, okay? For example, like 0.9999. This is infinity. This goes infinity. Yeah? Technically, this equals 1. Make sense? Good question. We're talking about limits. Because this one, it's a very complex, right? But there's a complex proof to say this is approximate. This is just 1. Right?
How?
For example, like it's hard to prove, but some people prove it, which might not be correct. Okay, this is not a precise proof. Okay, but
why do you say precise more than specifically?
Mathematically speaking, right, the way I show you, this is not a precise proof. Okay, for example, how do you prove this is 1? Okay, x equals 0.999 unlimited, right? Okay, 10x, if I times 10, what happened to this? 9.9, right?
Yeah.
Subtract, what happened? Taking x from 10x, what happened? 9x, right?
Yeah.
Taking this infinity from this, what happened? 9. X equals 1. Okay, there's a problem here. Because this is infinity, we can't just subtract. We can't just take it, right? How can you take away infinity from infinity? That's mathematically, this is not defined. Okay. Make sense? There's a problem with that, but technically this is 1. Okay. We'll mention that in the future. This is more the further math. Yeah. Probably when you learn the further math, you teach daddy. Okay. Yeah. Okay. We talk about this iterative approach, right? The key thing is that using the stack, we pushing the left nodes first, and then we take one out. We go to the right. Make sense? This is in order. The pre-order and reverse pre-order, we just converting the breadth search to, you're just converting the queue to the stack in the breadth search, and that would be the iterative approach of the pre-order or reverse pre-order, depending on whether we push the kids, left kids or right kids to the stack. Make sense? Yes? A equals iterator in order root, right? We know the how do we implement the in order using the recursion. And while true, the previous one equals the minus infinity, okay? Then you just take it, x equals next a none. If we haven't reached the end, iterator, right? This is the thing you asked yesterday. How do we know if it's reaching the end? If x is none. If this a has reached the end, we give the parameter none. If x is none, then break, okay? If the target bigger than the previous value and smaller than x, we return the same thing, yeah? Return the minimum of previous one and current value, which is x, and a key equals lambda abx y minus t, okay? Okay, and then we remember the previous value equals x, return previous, okay? In order, if we're using the in order, thing, right? Remember the yield from left, yield from in order left, yield root of value, yield from in order root of right. We convert into an iterator, right? We take the iterator, we check, we walk through the array. We basically walk through this iterator until we get into the point between the previous one. This is previous one. This is x here. The time connection is okay. Iterative approach is okay. Okay? Okay, what have you learned today?
I learned about this same thing as yesterday.
Yeah, so what's new today?
We learned about this. So we given a list, we find closest node to the target.
Mm-hmm.
And we want to know that it's in between these two nodes, or wait, sometimes it's just the node, and we want to know like when do we stop.
Okay, so what are the approach that we've taken today?
We taken the in order.
Yeah, in
so
order.
we put it in order, and because if you put it in order, it will be in order.
Yeah, and then the approach is the same algorithm, right? So we just taken this iterative approach using the stack. We push the left kids. Make sense? Yes? We go to the left. Once we don't go to the left, we turn to the right. And the next iteration, if this right kid has the left kids, you push them to the stack again. Okay? Make sense? Okay, that's it for today. Bye-bye. Bye-bye.